Hey everyone, today I'm gonna be doing something different. Instead of doing a legal problem, I'm gonna be talking about time and space complexity. The reason why I'm doing this is because time and space complexity are two very key fundamental topics that you need to know in order for you to master LeetCode as well as coding interviews. So to begin, I'm gonna be talking about space complexity. So space complexity is defined as the amount of time taken by an algorithm to run as a function of the length of the input. And when I talk about the time taken, I don't mean execution time. What I mean is the variation of execution time with respect to the input size. And the reason why we don't care about execution time alone is because different computers have different processing powers and processing speeds. So for example, you take the same algorithm and you take the same code and you put it on my laptop and you also put it on a supercomputer. Almost every time, the supercomputer will run it faster than my laptop. And so as a result, using time alone isn't a good or isn't a reliable measurement. So we're gonna use the variation of execution time with respect to the input size. And we're going to use something called Big O. So Big O is a mathematical approach to calculate time and space complexity. And for time complexity, we only care about average or worst case scenarios. Take this example. Suppose that we're given an array as the input, and we want to see if a specific value is in this array. Now, the best case scenario is that the element, or the value is always at the first element in an array, and so we can get constant time. That's the best case scenario, but this isn't very helpful or very practical. So instead, we will use the average case or worst case scenario. And one thing about Big O is that we don't care about constants. So one example is again, take the previous example where we're given an array as an input as well as a value, and we want to see if the value is inside the array. Suppose that the target that we're given, the value that we're given, is the middle element of that array. So that will be O of n over 2 time complexity. But because we don't care about constants, we will just use O of n instead. And another example is suppose we have 3 independent loops. Each loop has O of n time complexity. So if you were to combine all 3 loops, and again they're independent, it would be O of 3n time complexity. But we don't care about the 3. We just care, we don't care about the constants, right? So it will still be O of n time complexity. The point of Big O is to give like a reasonable estimate for the time complexity. Like we don't have to figure out exactly how much what the variation is. We just need an approximate, a reasonable approximate. So here are some of the commonly used time complexities. So constant time, or O of 1. And one example is accessing a specific index in an array. So for example, let's say you want to access the second index of an array. That would be like a constant time operation. The next time complexity is logarithm time or log time. And this is O of log n. So one example of this is binary search, especially on an array. The next time complexity is linear time. And this is O of n. And so one example of this is looping through an array. The next one is n log n. So for this one's kind of weird. There's no complexity name for it. It's just like O of n log n. And various sorting algorithms, such as quicksort, has either average time or worst time, so average case time or worst case time, or both, as O of n log n. I won't go too much about O of n log n in this video, once I start talking about different sorting algorithms, I'll bring up then, just because O of n log n is kind of weird. And finally, we have quadratic time, or O of n squared. And this is like one example that has O of n squared time complexity is a nested for loop. I'll show you that a bit later. So I really like this chart, this big O complexity chart. Now, if you notice, we didn't talk about O of 2 to the n or n factorial just because these are so bad that I didn't really want to mention them. O of 2 to the n, sometimes in like brute force, like in certain like brute force algorithms, like brute force backtracking algorithms or something, you might see that, but it's not very, like, it's kind of rare to see that. And O of n factorial, the only thing that comes to mind is Bolo sort, where you literally just like you just randomly sort the elements until you hit the correct until you hit the correct order. So I didn't talk about these two just because they're not used very much. But if the time comes, I'll definitely bring this up. So you can see the O of 1 or constant time and logarithm time are like the best, followed by O of n, and then O of n log n and O of n squared. So constant time. So what constant time means is that the algorithm's runtime is not dependent on the size of the input. So for example, like I mentioned, right? Accessing a specific index of an array, in this case, the first index. It doesn't matter how many elements are in the array. The runtime is still the same, assuming that like you don't get an index out bound 0 or something like that. Assume that the index is within the bounds. Like, for example, like if you have an array with 1 element and an array with 1 billion elements, getting the first element still takes the same amount of time. So you see how the algorithm's runtime is not dependent on the size of the input. So for logarithm time, this one I'm going to bring a bit of mathematical like intuition to this. So what this means is that the input size is reduced at each step. And if you think about log, right? And let me go to the whiteboard. Oops, sorry. So here, for log, so if you think of log in the mathematical sense, it's the inverse of the exponent, right? So for example, like 2 to the 3, its inverse will be log 2, 8. 2 to the 3 equals 8, if you didn't know. And so one way to think about this is, in terms of exponents, right? You have 1 times 2 times 2 times 2 equals to 8. And so now if you think about this log 2 to the 8, you can think of it as how log 2 to the 8 equals to 3. You can think of it how many times 8 needs to divide by 2 in order to reach 1. So for example, the first time 8 divided by 2 equals to 4. The second time, 4 divided by 2 equals to 2. And the third time, 2 divided by 2 equals to 1. So you see, we needed to divide, to divide 8 by 3 2s in order to get 1. And so in this case, right, if you think of log in the mathematical sense, you can see how at each step, we want to reduce the size of the input. And usually we reduce it by a constant factor. It can't be like the same amount each time because, for example, if you reduce an array by half, let's say you have an array of 8 elements, right? The first time you reduce the array by half, you drop 4 elements. The second time you drop 2 elements. So you can't reduce by the same amount, we can reduce by like the same factor. And like I mentioned, or like I showed in the chart, O of log n is a really good time complexity. And this is because if the input is huge, log n is still very small. So for example, log base 2 of 1,000,000 is roughly about 20. It's like 19.9 something. So you can see that O of log n, it's a pretty good runtime. And one popular example of, and also one popular algorithm that has logarithm time is binary search on an array. Now we're going to move into linear time, for O of n. So this means that the algorithm's runtime increases proportionally with the size of the input. So for example, looping through an array, we're doing a linear search on an array. And again, remember, we only care about average or worst case time complexities. And again, we don't care about constants, right? So even if the element is at the middle of the array, that would still be O of n time complexity, just because we dropped the 1/2. So before I talk about quadratic time, I want to mention about briefly mention about the O of n log n. Like I mentioned before, I'm not going to talk about O of n log n too much this time. So in this video, I will just say that many of the sorting algorithms, they have O of n log n runtime complexity, whether it's their average case or their worst case. So now for quadratic time, this means that the algorithm's runtime increases proportionally with the squared size of the input. And one example of this is a nested loop. And let me do an example. So let me move here. So suppose that we have this array. So suppose we have this array and we're gonna have a nested for loop. So something like this, like for so something like this, we have a nested for loop. So in the first outer loop, we're gonna encounter this one. In the inner loop, we're gonna go over all 5 elements, right? 1, 2, 3, 4, 5. Now, in the outer loop, we encounter 2. Again, in the inner for loop, we loop through all 5 elements. Same with the last three elements. Notice that we traversed the array in squared proportionality. Well, say proportional to the squared size of the input array. So here, right, the length of this array is 5, but here we traverse it like 25 times. So not 25 times, but like we how do I say this? We went through we went through the how do I say this? Like, we made basically 25 iterations or so. Right? So like you can see here, like here, this 5, 10, 15, 20, 25. So there's also like O of n cubed will enter the fourth. So like n cubed would just be like a triple like for loop, like for I, for j, for k, and then so on and so forth for like the other powers of n. So now that was time complexity. Now go to space complexity. So space complexity is the amount of storage an algorithm needs as a function of the length of the input. And then we're still going to use big O. Now space complexity is usually a lot more simpler than time complexity. Like you really see like O of log n for space complexity or O of n log n for space complexity. It's usually a constant, linear, or quadratic, or maybe some like other exponent of n. But for this video, I'll just talk about constant and linear. So constant space means that the amount of space is not dependent on the size of the input. So for example, take a look at this function, right? So what this function is doing is it takes in an array, like an array of numbers as input, and it returns their sum. So you can see we have a variable called sum, which is set to initialize to 0. And in this for loop, we just keep incrementing, so we just keep updating sum with each of the numbers in the array, and finally we return sum. Now, it doesn't matter how many elements are in this nums array. There could be 1, there could be 1,000,000, there could be 1,000,000,000, there could be 1,000,000,000. We would still only have this one variable sum. This sum would be the same regardless of how many elements there are in the nums array, right? So because of this, this would be an example of a constant space. Now, linear space means that the storage increases proportionally with the size of the input. And so for this example, right, this function takes in an array of numbers. And what it's going to do is going to square each number, and then it's going to return the array of all the squared numbers. So we have this res, which is set to an empty array. And in this loop, for each number element that we come across, we square it, and we append it to the res array. And finally, we return res. Now, in this case, the size of res increases proportionally to the size of nums. So if nums has 1,000,000 elements, so does res. If nums has 1 element, so does res. So you can see how the storage increases proportionally with the size of the input. So this is my video on time and space complexity. I hope you found it useful. I'm gonna link my PowerPoint in the video, and thank you for watching.